even at the back? Okay. So before going into the details of what we will do today, let's have a quick revision of what we did so far. So in lecture 1, we said that PN information is not enough. And then we motivated that we need to resum this PN information to extend the validity of post-Newtonian results. And after that, we said if we combine this post-Newtonian results with test mass results, we should be able to obtain something as an effective one-body theory. So we motivated effective one-body theory. And the key idea of EOB was to combine test mass with PN. Attach ring down. And then finally calibrate this waveform with NR. And when we attach the test, when we combine the test mass results with the PN results, we can basically split it into 3 building blocks. The conservative piece, radiation reaction, which were the forces that we added to the Hamilton's equation, and then the gravitational waveform modes. In lecture 2, we discussed how we model the conservative piece in the effective one-body formalism. Basically, we found that there is an energy map which takes the H real. H real is the PN information. Into some effective Hamiltonian, which is the effective Hamiltonian, which is the Hamiltonian of the effective metric. And then yesterday we discussed about the radiation reaction force and gravitational wave modes. And we said that if we resum the gravitational wave modes as a multiplicative decomposition, which is like this, we should be able to obtain the radiation reaction force as well, because luminosity is nothing but and the energy flux is related to luminosity as like this. And then if we put all this information in the Hamilton's equation that we wrote, we were able to obtain the in-spiral plunge waveform. But we could not capture the plunge entirely because everything that we did here was for circular orbits. And then we said we need to attach some sort of or add some sort of a non-quasi-circular ansatz to our waveform, this HLM, to be able to obtain the full in-spiral plunge waveform. And then we attached ring down to it. So how do we obtain the ansatz for this non-quasi-circular part, which I called as NQC, such that HLM is as this HLM times the NQC part, is by calibrating with the numerical relativity simulations. So there are few free parameters in our EOB setup. Some of them are here in the NQC part, and some of them are here in the effective Hamiltonian. And this way we will be able to obtain the full in-spiral plunge waveform, and we also attached the ring down yesterday. And everything that we did here was based on the PN information. So what is the current state of the art of PN? I will be only talking about non-spinning circular, non-spinning configurations, and not focusing on eccentricity as well for simplicity. So the state of the art of PN is 4 PN exact for conservative piece and partial results at 5 PN. Both of them are for the conservative piece. And now for the radiation reaction, or the force, or the fluxes. We have 4.5 PN information for the 2-2 mode, the dominant gravitational wave mode. And then depending on the other modes, the information obtained is less, suggesting that the effective Hamiltonian, or the L, or the flux, the luminosity, or the LM modes here in the EOB would also be based on this state of the art. So basically, H hat effective, H is also known up to 4 PN exactly, meaning that A potential is known up to this order, which is U5. In the tutorial, we have computed this A2, this A3, the 1 PN, the 2 PN, and the 3 PN information, but we never touched the 4 PN information. The reason is at 4 PN, starting from 4 PN, there is a subtlety in the PN calculation, or conceptual shift, which we briefly mentioned in lecture 1 as well. So the conceptual shift at 4 PN is the introduction of tail effects. And what are these tail effects? Tail effects are just non-local effects, suggesting that now the waveform at particular instant depends on the entire path. Let's think in terms of 2-point particles moving or orbiting around each other. If at this particular point it emits a gravitational waveform, these two objects, or these two point particles, are also creating a curvature, so it creates a sum potential. This gravitational waveform might be scattered, or or otherwise can go completely to far zones. So part of it can be scattered and can reach the source again. So it started at T0 and reached T1 once again at the source. So the source, now the waveform at this point is also dependent on the waveform emitted at T0. So basically suggesting that everything is dependent on the entire past history. And this is the conceptual shift. And this makes the computation in PN hard or complex, let's say. And the reason why the computations in PN at this order starts becoming complex is if these two times are coincidental, suggesting that T0 approaches T1 or T1 approaches T1, there would be some sort of a singularity in the system. And removing the singularity makes life complicated. So regularizing the PN regularizing the PN computations to obtain the finite part is complex, suggesting that after 4 PN results, the 5 PN computation by brute force would be more hard or more complex. So going beyond. And hence, the current state of the art is partial 5 PN results with full 4 PN results known in the literature. And it took approximately 45 years to reach this level of accuracy. But the gravitational detectors and signal to noise ratio are being continuously improved. So it suggests we need even more accurate gravitational waveforms. So what can we do? Is it the end of EOB? Do we need to wait for PN to be pushed to higher orders? Or do we only need to calibrate everything with numerical relativity waveforms? Because we said we can add arbitrary parameters here, which we can calibrate with NR. But what should be the functional form of these arbitrary parameters that we are adding? Are they dependent only on nu or nu square, or what kind of terms are they dependent on? So the few questions are, how do we build even more precise? NR only? Go to higher order in PN? The answer is not really. And just we discussed, because of the tail part, the PN, going to higher orders in PN is also complex. So what can we do? Is there something else? Is there something else is what we will try to answer and see if there is something else that we can use to inform this H effective, or basically these A, B, and Q potentials that we said are entering in the effective Hamiltonian. Before answering this, is there something else? Let's look again at A, the metric potential. We will come back at the computation of this A5 because of the presence of tail terms. Just in a minute. From the tutorial, it's clear how do we compute all these three terms, but with the presence of tail terms or non-local effects, how do we do this is something we will come to shortly. We know that this coefficient is 0. This is, I think, 6 nu. And this is also some function of nu. So in other words, we can write this as an expansion we can rearrange it such that it's an expansion in nu instead of u, where nu is the symmetric mass ratio. So rearranging A, we get that this is 1 minus 2u. Plus some term which is plus some correction because only dependent linearly on nu, some terms which are dependent quadratic in nu, etc. And this is exact in u. And we do this expansion such that it matches with the expansion over here, and u is 1 over r. So if we rewrite this A like this, now we have to see, is there something else available in the literature that maybe behaves like this, which is an expansion in nu instead of an expansion in u. Just one quick thing, maybe later. So what can we look for in the literature? In the literature, we can look for other perturbative techniques that are available. In the first lecture, we mentioned that depending on the part of the waveform that we want to study, there are various techniques. And even for the in-spiral, there are various techniques that are available that we can use. One of them you studied in last week, which was post-Newtonian, on which we built the entire machinery. In today's lectures, I think you are also studying about post-Minkowskian. So there are various perturbative techniques. To study the two-body problem. One is post-Newtonian, that we used entirely so far. And post-Newtonian is weak gravity and slow motion. And the expansion parameter here is v square over c square. But when we consider this assumption, we are not considering any assumption on the symmetric mass ratio in nu. So it's exact in nu. Now there is other technique called post-Minkowskian. PM, where we say we only consider weak gravity. No assumption on the velocity. And also there was no assumption on the symmetric mass ratio nu, so it's also exact in nu. Apart from these two techniques, there is also another technique called as self-force or gravitational self-force. In short, GSF. So in GSF, what you do is your expansion, you do not consider weak gravity, slow motion, or anything, but what you consider is there is a test particle which is moving around some space-time, and the expansion is in terms of the mass ratio m2 over m1, such that m1 is greater than m2. So you can consider that there is a test particle moving around a Schwarzschild black hole. This test particle's trajectory is only determined by this Schwarzschild black hole. But if this is not a test particle, it has some mass m. So its field will also start impacting its trajectory. So the basic idea is not only the primary object's field, sources the trajectory. So one can say that the Schwarzschild result is the leading order or the zero self-force result, such that there would be something plus a Q correction, and this something is zero self-force or the Schwarzschild result. Now this Q, being the mass ratio, can be related to the symmetric mass ratio here. Basically, we put Q equals m2 over m1. We can replace for one of the masses in that equation, and we will obtain that nu is Q over 1 plus Q squared. So we are saying that if there is an expansion in Q, it also becomes an expansion in the symmetric mass ratio nu. And that's what we try to rearrange A as. So we try to write it as an expansion in terms of nu. So it suggests that there is some overlap, and if we have some results from GSF, we should be able to obtain the results here by doing the PN expansion of the GSF results. And also other thing that we see here is we considered weak gravity, but no assumption on velocity. So in some sense, post-Minkowskian result should be able to capture everything that's in post-Newtonian. More explicitly, the PN-PM matching is like this. So you have Newtonian results, V square over C square, and the results in PM order like this, G square, G cube, blah, blah, blah. And these are post-Newtonian results. I can expand this in terms of velocity. So 1 PM terms enter at all the orders. G square can only start at 1 PN order. So this is like G cube starts like this. And this is 1 PN, 2 PN, 3 PN. So it says that if I have the 2 PM result, I should be able to recover the full 1 PN result. Or I can say that if I have 1 PN result, I should be able to obtain some coefficient of the 1 PM and 2 PM results. And also also additional terms that can enter in the system. That's the PN PM more explicit overlap. And similarly, there must be there is overlap between post-Newtonian and GSF, which is PN and GSF overlap such that if I expand this GSF results in small velocities, I should be able to recover something about PN. And if I have some results about PN, which gives me nu square kind of a term, I should be able to obtain something in gravitational self-force. So there is an overlapping regime implying something here can be informed by this overlap. And that's what we want to do. So using these because this matching is like at order by order in Pn, u square, u cube, and all these things. And that's what we have here, u square, u cube, u4. So we are saying that this a nu 1, which let's say is a full GSF computation coming for us, is some coefficient u square plus. And that's what Pn expansion is of GSF. And that should be able to capture the Pn results. So the idea is to use all these post-Newtonian, post-Minkowskian, GSF, and all the things that are available to us from the perturbative side, along with the numerical relativity results. Yes. For what? Yes. Yes, so you obtain from here that this is 0 SF and what you have is 1 SF. For GSF calculation, you need Q to be less than 1. But if I add this information in here, I'm not saying anything about Q anymore. Yes. Just to be clear that EOB is not doing self-force. EOB is not about doing an expansion in nu. It's just a rearrangement. It is PN. It's just rearranging. That's the keyword. Rearranging the A potential such that I factor the new terms out, nu square. I do not know this exactly. It's an expansion in nu. Okay. Yes, there will be. And I say that if from 1 SF, I know u to the power 6 contribution, I should be able to inform at least new linear u6 contribution in EUB. That's what the idea is. We have to say like, if we have GSF, let's say it's also a function of u, I need to say that it's an expansion in u. I need to expand it in terms of Pn sense. So it's, no, I need to do the Pn. It's not GSF. EOB is not a cell force. We only know a cell force up to a limited order. Only partial results, and we can inform. So basically, here are some terms. Yes. Yes, exactly. Okay, so I was saying that we should be able to use this cell force, post-Minkowski, and post-Newtonian thing. So using Pn, Pm, GSF, numerical relativity, and also MPM, which is multipolar post-Minkowski, which we will discuss briefly. Using all these formalisms to inform the EOB potential. A, B, and Q is what is called as tutti-frutti approach. Which literally means we collect all the fruits that we have and try to see if we can get some information. And this was developed by Binny, Damour, and Geralico in 2019. So that's what we want to study now, this tutti-frutti to inform the EOB potentials A, B, and Q. I mentioned that there is a conceptual shift at 4 Pn because of the presence of tail terms. It suggests that starting from 4 Pn order, the action of the two-body system should have both the local terms, which are the instantaneous terms acting at a particular instant, and non-local terms. Starting at from greater than equal to 4 Pn, they start entering. And I said these non-local terms are the problem, which I'm making the computations hard and the brute force computations to be hard. So what can we do? What should we do to obtain the EOB Hamiltonian? So the key idea would be to separate somehow this local piece from the non-local piece. So the key ideas of tutti-frutti. Separate out local and non-local. For simplicity, I will start writing as non-loc instead of full non-local. Use the self-force results. Note that self-force results have both the local and the non-local piece. And then finally, you also use the post-Minkowski results. As you might have studied in your morning lectures of this week, the Postman-Koskin formalism is particularly suitable for hyperbolic encounters. And for hyperbolic encounters, the natural choice of the gauge invariant variable, which we were again and again using to be the binding energy in terms of the gauge invariant frequency Ex, is actually the scattering angle. Because the key thing to do the mapping from EOB to from the real Hamiltonian to the EOB Hamiltonian is to find some gauge invariant variables or do a full canonical transformation. So from PM results, scattering angle becomes the gauge invariant variable. And for self force, the gauge invariant variable is the redshift. And this, I think you haven't covered in this series of lectures. And now we want to do this thing. Yes, it's the redshift observed by the observer outside, and this tau is the redshift is. One can imagine that this is the proper time of the point particle or the test particle that's moving around the primary object, and this is the coordinate time of the observer. So this is the redshift that we are talking about. So let's go one by one and see how do we use these key steps. So separating out the local piece and the non-local piece. Actually, the separation is quite clean. So we can write that this is local piece. At 4 p.m. and 5 p.m. I mentioned that the state of the art in PN computations is exact 4 p.m. results. So if we want to see the usefulness of this tutti frutti, we need to go to at least one higher order. So we go to 4 p.m., 5 p.m. order, and we separate the total Hamiltonian total action as local action plus the non-local action. And why we can do that, this clean split, it is because of the multipolar Postman-Kosky approach that I mentioned here. So what is this multipolar Postman-Kosky approach? Postman-Kosky, as I just said, is an expansion in G, which is weak gravity. And this multipolar is writing the source as in terms of the multiple moments. Which are the current multiple moments and the mass multiple moments. Using which we construct the gravitational wave flux in the first instance. And the idea is to combine both of them to get this clean splitting. So in PN calculations, what you do is, again, there is a scale separation. There is a near zone, there is a wave zone, and there is a far zone. You do PN computations in the near zone. So you obtain the PN results for the source multiple moments. So in the near zone, everything is a source powered. So this is source moments in PN sense. But the radiation is in the wave zone or in the far zone. In the far zone, you can't consider small velocity because gravitational waves are moving with the velocity of light. So you only can consider weak gravity because you are quite far away from the source. So in the far zone, you compute the radiative moments. But in PM sense. And the idea of MPM is to capture the propagation of the waves from the near zone to the far zone. Captures propagation of waves from near zone to far zone, which basically implies that it relates the moments, the source multiple moments, which I denote by Ij, with the far zone radiative multiple moments, which I denote by Uij for the mass type. And we have repeatedly said if there is a propagation of a gravitational wave from near zone to the far zone, there is some potential generated by the binary itself. And some of the gravitational wave is being scattered by this potential, which captures the tail effect. So one is saying that MPM should capture the tail effect. So it cleanly captures the tail effect by relating the source multiple moments with the radiative multiple moments, hence allowing us to do a clean separation of the action from between local and non-local pieces. And if we have the and this tail effect or this flux that how this relation is done is based only on the leading order PN, leading order multiple moments. So we get this piece which was hard to compute for free using MPM. And what does this piece look like? The S non-local. Looks like V square. There is some M mass. So this is the this is how the non-local action would look like, and this F1PN is nothing but the flux that we saw in the previous lectures. So it's like the flux, which is made up of the Iij and Jij. So let's look at how and why we should get this structure of the non-local piece. I'll come to it one by one. We will look at the full term one by one. So why there is G square? We said that the tail is like one propagation being scattered back. So 1G, basically linear G, comes from the first or the ordinary interaction. And this Gm factor, where m is not the total mass of the system, but is actually the total conserved energy, which we saw in last lectures to be the MADM, because that determines the curvature of the potential that's generated by this binary system. So this Gm comes from the potential from which these waves are scattered. Now we have this kernel, which is 1 over t minus t prime. Let's say that this is t prime and this is t. This is to capture how strongly the dynamics at time t is related to the dynamics at time t prime. And this integral over t is nothing but it is just the action is being dt times L. And this dt prime, the second integral, is actually capturing the effect of the entire path at that particular point. And now, what is this PF? I mentioned that if the two times are coincidental, then there would be divergences in the system, and we need to regularize the system. And this PF is doing that. It's a regularizer called as Hadamard-Partikley regularization approach. One can use other regularization techniques as well. For example, dimensional regularization, which you might have seen in some of your lectures this week or the last week. And the idea of this Hadamard-Partikley is to remove or subtract the divergent piece that's coming from this integral, so that we only obtain the finite part. There is no special reason why we use this. It was just used in the literature for the leading order correction. So at leading order, we try to stick to it, but one can use other schemes as well. And this 2R1 T over C is actually the scale of this regularization scheme that we are using. And R12 is nothing but the radius. And since MPM is based on or is done in harmonic gauge, so this R12, the radius, would be the harmonic radius or the radius in harmonic coordinate. And this final piece, which I said is this F1PN split, is the flux, and it looks like, I mentioned that it should be made up of the source multiple moments, so it looks like this. Yeah. When you do the computation for the energy fluxes, what you consider is both these multiple moments, the source multiple moments are at the same time, but now you want to see the effect, which is like this. So they should be at different times, like t and t prime. And that's the reason why we also have split written here. Otherwise, it would just have been a normal flux. And from this action, we should be able to obtain the Lagrangian, which is nothing but this whole term. This whole thing becomes the Lagrangian of the system. And from the Lagrangian, we can obtain the Hamiltonian. Since there is no P dependence directly in F1Pn, so Lagrangian is nothing but just equal to minus of the Hamiltonian. And now the question is, how do we capture this known locality that we have here coming from the time integral into this effective Hamiltonian that we wrote here? And this effective Hamiltonian is made up of the effective potential or metric potentials metric potentials A, B, and Q. So the idea is now the question is, how do we capture that non-locality into these three potentials? There are two ways in which we can do that. Yes. Yes. This is the third time derivative. Yes, but if there could be velocities, but there is nothing like Q dot kind of a thing. And if we do the analysis, there we see that this do not contribute. These P dot are not local, so we can set them to somehow 0. Okay, so what I was saying that how do we capture this this thing? There can be two possible ways. Capturing non-locality in A, B, and Q. There could be two ways. One way would be, I just introduce some non-locality in here. I say that A is local plus some time integral function. So I say that A, B, and Q, or let's say H hat effective, should be like local plus some non-local piece. And here I'm introducing the non-locality. Exactly as the way in the two-body Hamiltonian. That's one way. The other way could be, if somehow I can reduce this non-locality into local thing, then I should be able to do the matching, because I know how to do the matching of the effective Hamiltonian to the real Hamiltonian if there are only local contributions. The second thing could be reduce the non-locality into local and then do the mapping. And this is what we will discuss, and this is the preferred approach. So that both the non-local and the local piece are at the same footing. And how do we do this reduction of non-locality into the local thing is, the idea would be to reduce non-local into something which is local. I mentioned in lecture 2 that there are various ways of doing the mapping from the effective Hamiltonian to the real Hamiltonian. One of the way that I mentioned was using action angle variables. And this was the way that's how EOB was first introduced. And if we write this non-local Hamiltonian in terms of the action angle variables, we will be able to do the reduction of the non-locality into the local Hamiltonian. So doing the transformation of R, PR, P5, phi into action angle variables. For simplicity now, I will call them as AAV. Once we write this non-local Hamiltonian in terms of action angle variables, I can order reduce it. And what I mean by order reduction is that I had this Iij at some time t and Iij at some time t prime. This t prime is nothing but some t plus some parameter tau. And if I can express this source multiple moments in terms of the source multiple moment at time t, I'm able to order reduce it. So everything will be in terms of time t then. So express. So the basic idea is express variables at time t only. Which implies t prime is some t plus tau kind of a reduction is what I want to do. After I do this order reduction, I can express this action angle variable in terms of the eccentricity and the orbital separation. So and the semi-major axis, let's see. A and E. And once I express this, I can do the expansion of whatever I obtain, which is basically do the expansion of this Iij and Iij t prime in terms of E and A. Expand in powers of eccentricity. And when I do this expansion in powers of eccentricity, what I would obtain is that this Hamiltonian is just periodic in mean anomaly. It's periodic. If the Hamiltonian is periodic, I can do the orbit averaging, and that will remove the integral over, let's say, the period, and hence I will be able to obtain the local piece. So eliminate this periodicity. So from the real side, I have obtained the H local, which is order reduced now. From the H non-local. I can play the same game here on the H hat effective, on the H effective side. I can express it in terms of the action angle variables, then do the expansion in eccentricity, everything, then I will obtain H effective in terms of action angle variables, and then in terms of eccentricity, doing the eliminating the period. So I should be able to obtain the H effective non-local here as well. And when I do this reduction of H effective to H effective non-local thing, what I also do is, just like the real Hamiltonian, I will split the effective Hamiltonian as effective Hamiltonian coming from purely from the local piece, and the effective Hamiltonian coming from the non-local piece, which basically implies I'm splitting A as a local piece plus a non-local piece, similarly for the other metric potentials as well. So my this H effective non-local will only be dependent on this A non-local piece. And once I do the matching of this non-local with this non-local piece using the energy map that I have here, I should be able to exactly obtain the non-local A information. So MPM gives the A non-local piece information. Oh, by order reduction, I mean, so we have the source multiple moments at 2 times, t and t prime. If I can write this t prime in some function of t, I'm reducing the T prime as just T things, and everything will become a constant thing. Everything is now in terms of T. So I have order reduced this, in some sense, I have order reduced this non-locality into the local thing by writing everything at the same instant T. Okay, so we have obtained this from MPM, this A non-local completely. And we can obtain it up to 5PN as well, which is not known, or which was not known from the exact PN results. So that's one piece. Now let's look at the second step that we mentioned. Second step is cell force. Basically, the GSF results to be used to obtain something in these A potentials, B potential, or Q potential. And the cell force computation in itself is a combination of local piece and non-local piece. So what it tells us is, if there is some non-local piece coming from cell force computation, it should match with whatever results we are obtaining from the MPM formalism. And it gives us a check of whatever we're doing from MPM. Is it okay? And it gives a check of various perturbative techniques that we have had. For simplicity, now we will focus on circular orbits. The reason why we will focus on circular orbits are computations are easy. Or basically tractable. And from this effective Hamiltonian, if we are in the circular orbit, we say PR is 0. So this B disappears. This Q is also a function of PR. We wanted Q to be a function of PR so that for circular orbit, everything is quite simple. So all the information is now contained in this A potential. So it's quite easy. It's tractable, let's say. We have isolated the potential A, as that is the only potential that contributes. And we also know for circular orbits, we can express everything in terms of the gauge invariant frequency X. So that is also we are familiar with. And finally, for the realistic scenarios that we observed so far, we didn't expect to observe eccentricity. So circular orbit limit is a good thing to start with. And I said that the gauge invariant quantity that we will focus or we will study in cell force is the redshift. Which I will denote with ZSF, let's say. And what is this ZSF or the redshift? As I was mentioning initially, if we consider a point particle or a moving around a primary mass, and if there is a clock attached to the point particle, the proper time of that point particle is, or the proper time measured in that clock is tau. This is primary M1 and this is secondary M2. Proper time tau. And if I'm an observer far away, my coordinate time is t. And the ZSF or the redshift is d tau over dt. And this tau would be less compared to t, because this particle is in deep gravitational potential well. So the clock or the proper time would be less compared to the coordinate time. Let's do an easy calculation of how we obtain this self force. I said that zero self force is nothing but considering a Schwarzschild case. So let's consider a test particle moving in sorry? Yes, that I will use. And that in some sense is like 0 SF. So ds square, the line element is g mu dx mu, where we know g mu is 2 over r square sine square theta. Only diagonal and everything else is 0. For simplicity, again, we will focus on circular orbits. R equals constant and also equatorial. Theta equals pi by 2. The line element is related to, again, the metric convention that we are using is minus plus plus. The line element is related to the proper time like this, which is chi mu dr square, because only diagonal elements are present. We assumed the circular condition, r was constant, so this disappears. We also consider equatorial orbit, theta was pi by 2, so this disappears. And what we have only is the time component and the pi component. And if we insert in the equations here, what we get is we get that d minus of d tau square is this. But we also have Hamilton's equation, which relate d phi with omega, the frequency, the orbital frequency. We know d phi over dt is omega. We can put in here. And from Kepler's third law, we also know that r cube omega square is equals to m, or omega is equals to m by r cube 1 over half. If we put in everything here, what we should be able to obtain is d tau square is equals to we should be able to obtain this expression. One can check it easily. So the times dt square. So we have d tau square is 1 minus 3 over r. So ZSF, which would be d tau over dt, or 0 SF, the redshift. In terms of the gauge invariant frequency x is 1 over r at the leading order. So this becomes 1 minus 3x. And this completely makes sense because at the light ring, the time clock goes to 0. Now this is the 0 SF calculation. And similarly, from the self force result, we should be able to obtain the 1 SF as well. So ZSF is plus higher order terms. So we have the redshift from bigger. Okay. Is this equation okay? Is this equation okay? So what do we have finally is this ZSF is 0 SF computation that we just did from Schwarzschild, and then from self-force we will have the 1 SF computation plus higher order term. So the total redshift from the SF self-force computations would look like this. We also wrote a relation which was mu equals q square, q over 1 plus q square. So at leading order, we can say that it's just a correction which is in powers of nu instead of powers of q. This is everything done on the self-force side. Now we need to do something similar on the EOB side as well. Or how can we relate this? The first question would be, how do we relate this self-force computation with the energy or the Hamiltonian, which we want to find out, because Hamiltonian gives the dynamics of the system. So let's see how do we get that. Now the question is relating this ZSF with the Hamiltonian H real. How do we do it? We use the first law of binary dynamics, or like we can say as first law of point particle binaries. So we use first. So we use first law of point particle binaries, which help us in relating the ZSF computation with the real Hamiltonian, or the redshift with the real Hamiltonian. This was given by Lettiak, Blanchet, and Whiting in 2012 for circular orbits. And the generalization to eccentric orbits is also given by Lettiak in 2015. And the statement of this first law of binary point particle binaries is, if we change the mass of the binary by keeping the frequency constant, we should be able to relate the self-force with the H real. So the statement says that if we vary the mass, keeping the frequency to be constant, the redshift is related to the energy and angular momentum using this formula. Yes, the same thing we had for X. Let's say for simplicity, we put it as omega. It's the same omega that we had initially. So basically, this is the statement. And now we have to use this Z to find this H and this J. And if we have this H and this J, we should be able to relate it to this H hat effective and the J effective coming from the effective one body system. This is a theory. This can be proved. It's a law. You can start with the circular orbits, and you can see that this can be proven. We give Hamiltonian in tutorial 1, which is basically the rest mass plus the binding energy. Binding energy is given in the tutorial. We can find the J, and we know the redshift from self-force computation. And if we put in all this together, we should be able to obtain this law here. And this is only for the circular orbit. dimension. Which is PR equals 0 and R equals constant. This Hamiltonian, this angular momentum, and this Z, and A is 1 and 2 because we are considering binaries. So A is to denote one body and the second body. This whole thing is a function of M1, M2, and the frequency omega for circular orbits, because omega is related to the frequency x. So everything has to be a function of M1, M2, and omega. And then we can map it to be a function of the total mass m, the symmetric mass ratio mu, and the gauge invariant frequency variable x. When we do this mapping from M1, M2 to M1, M2 omega to m, nu, and x, what we obtain is that each self force, the energy that would be coming, or the H that would be Hamiltonian that would be coming from the self force computation, is equals to I think that's the correct relation. X square is omega cube. I cube is x cube is equals to omega square. Yeah, so this is correct. Minus so when we do this change, what we will obtain is that the Hamiltonian of the self force is related using this first law as Hamiltonian self force minus this thing minus 2x over 3 multiplied with the derivative with respect to x of this first term, which let me call it as sum m of x. And here prime denotes a derivative with respect to x. So that's what we obtain. Actually, I think I made a mistake. I think it's correct. So this is how we obtain the self force computation. And this H self force we said can be related to H effective using this energy map. And putting the ansatz now, which was A is equals to 1 minus 2u plus A coming from the self force computation nu, I should be able to obtain the A self force. Because here I can write H self force in terms of A self force. It's the similar thing that we did in tutorial 2, that we have H hat effective in terms of the metric potentials A2, A3, A4. And on the other side, we have the H hat effective coming from the two-body system. So if we combine all these things, we should be able to obtain the self force correction to the metric potential A. And what we have from here, what we get from here is A self force as A self force local piece and A self force non-local piece. And this can be mapped to the MPM results, and the other thing becomes the new information from the self force side. So that's what we do in the self force. Now, if we want to consider eccentric orbits, in addition to this result, what we would have now is we will have this additional contribution coming from the radial potential. And this radial potential is nothing but PR. And we said for circular orbits, PR is 0, so this didn't contribute. But now for eccentric orbits, this would contribute. And now using the same thing, same game, we will be able to also obtain this V and Q parameter, V and Q metric potentials, which we could not obtain when we were fixing or focusing on the circular orbits. N is the radial frequency, which is dependent on the orbital period. Yes. Yes. So this is what we did with the self force. Now there is the final step, which is PM results. We will start with PM results today, and hopefully we will be able to see something more tomorrow. Sorry, I didn't get the question. Oh, you have for India. This R is, or I wrote as IR. Yeah, it's in terms of the action angle variables. That's why I said that this is a radial action. And this J is coming from the angle part. Yes. We will do it in the tutorial today, but the reference, you mean how to do this computation? How do you get the non-local part of the self force? Maybe I can briefly say about it. The reference I don't remember. It's some paper by Baralse, Bonanno, and others. And there are papers by Binney and Damour. One can check Binney and Damour 2019 paper as well, where they first gave this tutti frutti thing. And there are papers by Damour himself from 2007, 2008, which are only about self force computations. But they don't use this first law, because first law was given recently in 2012. But after that 2012, there are multiple papers that one can check. But I think this should give you all the references that you might want. And how do you get the non-local piece? You asked. So the non-local pieces, when you do this self force computation of Z, so ZSF is in itself, we said Z0SF plus times Q plus higher order terms. This Z1SF is Z1SF coming from the local contributions, and then there is Z1SF coming from the non-local contributions. And the characteristic of this non-local contribution is it has logarithms present in the system. So you can identify from any of the self force paper that this everything that comes here, which is like some U squared plus U cube plus blah blah blah, purely as a polynomial in U is the local contribution, and anything that would come with log of U plus U log of U, anything that is the non-local piece. And from the effective Hamiltonian here, you are also writing the A as A local plus A non-local. This A local is something we have seen multiple times, which is 1 minus 2U, A 2U squared. And this A and non-loc becomes, let's say, it starts at 4pn. So A5, it starts at 4pn. So A5 logarithmic of U plus A6 U log of U plus higher order terms. And when you write this, rearrange this A instead of the Pn formalism as this self force kind of a thing, you can write it as A equals And now this ASF is now split as ASF local plus ASF non-local piece. This is similar to what we have here. And this ASF non-local is similar to what we have here. So you can do the matching one by one. That's how you do the matching of the non-local piece with the local piece. Okay. Let me just briefly mention about scattering or the PM results. That's what we have here. And one good thing is we should be able to verify that whatever we get from PN is also something that we can get from self-force. If there is any discrepancy, it says that there is a discrepancy either at the self-force level or the PN level. But up to 4 PN, PN information has been extensively checked by various groups. So one has to be a bit careful about self-force and all these things. Let me briefly talk about the final step, which is the scattering information. Which is the Postman-Koskin expansion. And Postman-Koskin expansion is in G. And we made a grid structure which said like, we have Newtonian, 1 Pn, 2 Pn, G square, G cube. We made this grid structure. We said that there is an overlap between Pn and Pm information. And the gauge invariant variable in PM expansion is the scattering angle because we focus on hyperbolic orbits. As you might have seen in the course in the morning today. And this scattering angle is related to the EOB Hamiltonian because what we want to do is we want to obtain this EOB Hamiltonian. So we should be able to first find the relation which relates the scattering angle that we have with the EOB Hamiltonian. When we do the Hamilton-Jacobi equation, we can do the separation of the action as constants of motion plus the radial action that we will have. And this radial action is related to the scattering angle as follows. This is the relation between scattering angle and the radial action PR, or the radial momentum PR. And this pi is here so that we can have zero scattering. This is J. This is J, angular momentum J. S, as we saw, was that's how we split the action because these are the constants of motion. The action is invariant under time translations and rotation. So we can obtain these two things. And if we consider the variation with respect to phi and with respect to r or j, basically, we should be able to obtain this relation. Sorry? Yes, pi is just an is just a normalization thing so that you have zero scattering angle. If the no, it's just pi. So you have zero scattering angle if there is no other object present in the system. And just one quick thing that I will mention. From this action, from this Hamiltonian that we have here, we can invert this Hamiltonian, express this PR in terms of this HIR effector. We have chi. We have this PR as this H if thing. In EOB, this H effector is nothing but just gamma, which is the Lorentz factor. And if we remember the DIS picture that we studied, this gamma is P1 dot P2 divided by 2 M1 M2. And if you remember the DIS picture, this is what effective Hamiltonian was coming out to be, because we had H and this E total square was the Mendelssohn variable, which was P1 plus P2 square, and hence we were able to obtain that this is nothing but basically the gamma. For hyperbolic encounters, that would be the case. So we know the Lorentz factor, which would be 1 minus V square over C square. We invert this expression, we will be able to obtain A, B, and Q given the scattering angle, which we will know from the 1 p.m. computation. Tomorrow, I think I'm short of time. Tomorrow, I will discuss about this in more detail, and I will also discuss about the fact when we were doing this PN computation of obtaining this A2, A3, A4, etc. We said that A2 is 0, A3 is just linear in nu, A4 is also linear in nu, and we said there must be some hidden symmetry in the system. What is this hidden symmetry? How do we know that what is the structure of this EOB Hamiltonian is going to be? And another thing that we found from the PM computations or the computations that you are doing in today's morning lectures are of the impulse and hence scattering angle. We find that the 1 p.m. and 2 p.m. scattering angles are independent of nu, suggesting that they can be completely determined from the Schwarzschild test mass limit. This thing combined with this thing suggests some hidden structure, which we will discuss tomorrow. And then we will discuss how that hidden structure can help us in finding other terms in the H effective. Yes, so thank you for the attention.